Welcome to our introduction on related rates. The single most comprehensive concept up to this point in calculus is the discussion of related rates. It'll test your ability to properly compute derivatives with respect to any variable in scenarios where you'll first need to analyze a situation, then create your own equation to solve for a certain variable. Sounds tough, right? Well, it doesn't have to be. In this video, I'm going to show you how to tackle any related rates problem flawlessly, which will help you dominate optimization as well. The reason both of these topics are mentioned in this video is because they're essentially one and the same. Think of real numbers versus integers. While all integers are real numbers, not all real numbers are integers. And so while all optimization problems are related rates problems, not all related rates problems are optimization problems. Optimization is within the conversation of related rates, but narrowed down to situations where we always look for the best or optimal outcome, as opposed to solving for a particular variable, which we do in related rates. So before we complete any problems, here's my guideline to solving any related rates problem ever. The central idea behind related rates problems is to analyze, formulate, and derive so that we can solve. And so one more time, we want to first analyze the situation, formulate an equation that represents the situation, and derive our equation to solve for the unknown variable. So let's go ahead and fully expand on that so we have a nice, good general guideline. So when we analyze, what we want to do is analyze the situation. When we do this, we want to go ahead and write down any given information. With that information, we want to identify all of our given measurements and do so with units if needed. We want to also ask ourselves which measurements are variables and which ones are constants. We'll know if it's a variable if it's changing or if it has a rate, and we'll know if it's a constant if it's not changing or if it's just part of the problem in some way, shape, or form, and it'll be pretty obvious to tell if it's a constant. Next, we want to ask ourselves, what are we solving for? And we want to write it out. We want to represent the variable that we're solving for. And that takes care of analyzing. After we analyze, we're ready to formulate. So to formulate, we first want to represent the situation with an equation. We always want to take note of any shapes, any visuals or diagrams that we are given. And at this time, you can input any of your constants. Step 2, all the variables in your equation, all but one, should be known because one of them is what you're trying to solve for. And if not, if you have two variables that are unknown, try to write one variable in terms of the most important, because these rates are probably related and you may be able to write one in terms of the other. Lastly, we want to derive. So first, what are we taking the derivative with respect to? We always have to ask ourselves that, because we could have a changing rate with respect to time, with respect to a certain variable, maybe a radius or a side length or whatever it may be. But we always want to be careful and note what we're taking the derivative with respect to. Next, after we identify that and we have our equation, go ahead and take the derivative of both sides. We want to go ahead and substitute known values and solve for the unknown afterwards. And that's it. Once we solve for that known value, we want to go ahead and make sure that if this is a free response problem, we want to make sure we give a conclusive statement in complete sentence form. And that takes care of that guideline. And I know it was a lot to take in, but the more we practice, the more it will become part of every related rates problem you complete, and it'll become second nature eventually. So now, let's go ahead and apply this thinking. Let's go ahead and say we have this problem. In a circle whose radius is growing at a rate of 2 meters per minute, calculate the growth rate of its area when the radius is 10 meters long. So, let's go ahead and begin by analyzing the situation. Let's go ahead and write down all of our given information. So reading the problem again, I saw that we're dealing with a circle. It says in a circle. So next I want to ask myself, well, what about the circle? They say the radius and I see area. So just keep that in mind as we move forward. We see that we have the radius is growing at a rate of 2 meters per minute. So let's think about that. Normally when we think of a radius, we think of just a measure. So we think of a radius which equals blank meters. Here we see meters per minute. Now that's a little odd. And so that wouldn't be the radius. That's actually the rate at which the radius is changing. So that'll be the derivative of radius, or dr, with respect to what though? That's what we want to ask ourselves next. take a look. We have 2 meters per minute. So that's time. We're taking the derivative with respect to time. And so the rate of change of the radius with respect to time, in this case, is 2. We don't exactly know what the radius is right now, but let's go ahead and keep looking. We're asked to calculate the growth rate of the area when the radius is 10 meters long. Okay, cool. So we actually know the radius. It's 10 meters. And then our radius is changing at a rate of 2 meters per minute. So far, so good. And again, we're solving for the rate of change of the area. So if we're looking for the rate of change of the area, that'll be the derivative of the area with respect to, remember, time. We figured that out. It is time. And that's what we're looking for. We don't know what it is, and we don't know what the area is at this time either. But you'll see in this problem, this doesn't exactly matter. Before I continue, it's just important to note that we have a radius and we have an area, and actually both of these are changing, so both of these are variables. So it's important to note that now. Up next, we want to go ahead and represent the situation with an equation. So now we're formulating. Well, in the problem, it's said that we're dealing with a circle, and we want to know about its area. And so we can go ahead and represent this with area equals, well, the area of a circle is pi r squared. Just like that. And at this time, we can't replace any of the variable values, because we could replace the 10 meters for the radius. We would get the area at that time, but we're not looking for the area at that time. We're looking for the rate of change of the area at that time. So honestly, this isn't exactly relevant. And I'm going to solidify this in just 1 second. And next, we can't input the radius's value because the radius is changing. The radius is changing, so it's not a constant, so we can't just put that in. And so yeah, we have 2 variables so far in this equation. We know one of them, so we could solve for this, but like I said, the area is changing, so we don't even need to worry about that right now. So it seems we're ready to move right into our derive and solve step. So we want to ask ourselves, what are we taking the derivative with respect to? Well, funny enough, we answered this question earlier because it was necessary. And so it just so happened that we solved this earlier. We're taking the derivative with respect to time. So I'm going to go ahead and do that. Let's go ahead and take the derivative of both sides with respect to time. So this means that we'll have the derivative of area with respect to time, or the rate of change of the area with respect to time, is equal to the derivative with respect to time of pi r squared. And a lot of my students, they get a little freaked out when they see pi. They think pi might be a variable. It's all good. Don't worry about it. Pi is not a variable. Pi is a constant, just like e, just like any other number. We're just dealing with the r squared. So essentially, the derivative of r squared with respect to time, always remember the chain rule. Always, always, always. So let me just go ahead and work over here. dA dt equals, so we essentially have something squared. The derivative of something squared, let me just put the pi there. The derivative of something squared is going to be 2 times that something raised to the first power multiplied by the derivative of that something with respect to time. And I'm just following my chain rule here. If you're having a little trouble with the chain rule or following along so far, I would definitely suggest looking at my videos on chain rule and mastering the chain rule. That way we can come back and do this confidently, as well as implicit differentiation. So, looks like we're good to go. All we have to do is do some simple simplifications here. We are searching for the derivative of the area with respect to time. We have pi to r. Do we know what r is? Yep, it's right here. Do we know what the rate of change of r is, or the rate of change of the area is? Yeah, that's right there. So I think we're pretty good. It looks like we're pretty good. So we can go ahead and solve for dA dt. All we need to do is substitute for our values, or substitute our values in. So in doing so, the derivative of area with respect to time is equal to pi times 2 times r, which is 10 meters. It's important to note the units. We have 10 meters. Multiplied by the derivative of the radius with respect to time, which is 2 meters per minute. Awesome. So now all we got to do is just put it all together. So pi times 2 times 10 times 2. 2 times 2 is 4, times 10 is 40, 40 pi. So our area is changing at a rate of 40 pi. We are not done though. We need the correct units. Remember earlier, our radius was in meters. Our derivative of the radius with respect to time was in meters per minute. So essentially, we're multiplying meters times meters all over minutes, which is meters squared per minute. And this makes sense because the area, an area should be in square units. And if it's changing at a rate, what's going to be the square units per time? And so yes, this checks out. So in all, this process works. I didn't exactly follow it to a T because some things were a little more obvious at the beginning of this problem. Like looking at what we're taking the derivative with respect to, that was fairly obvious in this problem because we were given meters per minute. And that's one of the easy ways that we can see what we're taking a derivative with respect to with related rates problems. So, in all, I hope you found this introductory video helpful. There are plenty more videos that you can look at. That way you can continue mastering related rates and then implement that into optimization. Up next, in the next overview video, I'll be giving an overview of optimization with a very similar guideline as to how we can solve any optimization problem. So, until next time, go ahead and watch the next videos, practice and master, and I'll see you in optimization. Have fun.